Başladım.
Got it. Okay. Great. So today we are very happy to have Umut GÜRSOY from Utrecht University as our speaker. So although I don't think he needs an introduction, let me give a brief introduction anyway. So Umut finished his bachelor's degree at Istanbul Technical University. Before he started his master's work with Gebner at Weizmann Institute, and then after that he moved to MIT for his PhD and worked under the supervision of Daniel Friedman. And after he graduated, after he obtained his PhD, he moved to Europe for his first postdoctoral position at École Normale Supérieure or Ecole Polytechnique, and then moved to Utrecht University for a second postdoc, and he was at CERN as a research fellow from 2010 and 2012, when I was also a fellow at CERN. So we spent 2 years together there. And after a brief visiting scholar position at Leuven, he started his assistant professorship at Utrecht University in 2015, and he's been there since then. And today he will be talking about hydrodynamics of spin currents. Okay, thank you.
Okay, well, thank you very much for this nice introduction, John. Can you, by the way, if I speak like this, can you all hear well? Is that good? Good. Yeah. Okay. So, well, my apologies to some of you if you have seen this talk before, but this is don't worry, because that's going to be something new towards the end. So, well, I think, well, I just want to say first of all that I think this was a great idea to have this joint seminar series in theoretical physics. So I think I hope this will continue, and thanks for all the efforts for making this up. I mean, just all after Corona, probably it will be a good idea to continue this, if there's going to be any after Corona, that we don't know, but let's see. So I will be talking about the spin currents today, and this is a work that is based on these two papers. The first paper here, I will be mostly talking about this paper and some ongoing work as well. Again, with the same authors. Amos Yarom is a professor at Technion. Domingo Gallegos is my student here in Utrecht, who's graduating. And with Domingo, we had an earlier paper last year, and that was essentially that was dealing with the holography, the gauge-gravity duality of the spin currents. And as typical in this kind of work that we do, we first do the holographic approach first. So this is a bit like contrived way of doing things. You would think that, hydrodynamics should come first, but holography provides a lot of insights to construct the hydrodynamic expansions and actions, as I will tell you more about later. But this talk itself will be just about hydrodynamics. Okay, so let me first, and please just interrupt me at any time. Let me first give you some brief motivation for this work. Spin transport is playing an increasingly prominent role in different studies in theoretical and experimental physics. In a very wide range of topics, like from spintronics, especially liquid spintronics, to graphene, Dirac-Wild semimetals, and all the way to high energy physics like quark-Coulomb plasma, where there's spin of quarks are playing some important role, and they can be transported, and they have some observable effects, as I will explain in the next slide. And ... This ... is wherever spin degrees of freedom are playing an important role, wherever they are strongly correlated, so that they can be described as some kind of collective transport phenomena. Okay, so their flow. So all of this, what I will be telling you today, potentially will be applicable to all these different kind of problems. And so this ... For example, the most interesting one there, I would say, is the neutron stars astrophysics, because we know that the cores of the neutron stars are believed to have some quark matter in it. And when we observe gravitational waves coming from like two merging neutron stars, or a neutron star merging with a black hole, the gravitational wave will potentially carry information about all kind of transport phenomena happening in the neutron stars, and one of them will be the spin transport. And spin there is quite important because these are very rapidly rotating objects as well. Okay, so but for this talk, the main motivation is coming from this recent observation in the heavy ion collisions. So heavy ion collisions are collisions of lead or gold atoms of these beams. Ongoing experiments at RIC and LHC. And in these experiments, what you all know is that when you collide these two atoms with very large atomic structure, so both lead and gold have a large atomic structure. So here in this is a schema of this collision, and what happens is that you produce some kind of quark-gluon plasma. So this is a plasma. These are very strongly correlated collection of quarks and gluons, which behave like a plasma essentially. It's indistinguishable from a plasma because if you compute its shear viscosity, you're going to find that this is one of the best, almost perfect fluids that we have in the universe. And in a particular off-central collision, when there's some initial angular momentum in the system that is carried by these beams, this because of angular momentum conservation, that will be translated into the global rotation of the produced quark-gluon plasma after the collision. And that rotation, essentially, the idea here is that rotation, because of a spin-orbit coupling in QCD, it orients the spins in the system, the spins of gluons and quarks, mainly quarks, and that produces some kind of coherent spin current in the direction of the angular momentum. Okay, and that is something that you can try to see if this global polarization, spin polarization, can be observed. And there is a particular particle, some hadron called the hyperon, and this is a baryon, and these hyperons are self-analyzing particles in the sense that if they have some initial polarization, and their initial polarization is correlated with the proton, with the momentum of the proton that they decay into. Okay, so this is the polarization vector, and this is the proton, the momentum of the proton. There is a fixed angle between them, and so by looking at the daughter protons observed at the detector, you can essentially reconstruct the initial spins of these hyperons that were in this produced right after the plasma decays into hadrons. And from there, you can essentially read off how much vorticity there was in the original fluid, in the quark-gluon plasma. And then you find an astronomic number. Okay, so here in this plot, what I'm showing is the polarization, the global polarization of these hyperon particles. There are lambda hyperons, there are lambda bar hyperons. They differ in electric charge. So as a result, because also there is a magnetic field in this game, which I'm not showing here, there is a difference between their polarizations. I will be ignoring the magnetic field in this talk. So I'll try to reproduce the mean of these two curves, just the average of these two for the hyperons and the hyperon lambda bar and lambdas. And here you see the distribution, the particle distribution as a function of polarization and this angle theta. Okay, so and this coupling constant. So here, this is as a function of the center of mass energy. So the main motivation of this talk is to reproduce this directly from entirely from a hydrodynamic description. Okay, so there is a very clear phenomenological motivation that we have, but this motivation can be extended also to other systems, because the same kind of phenomena can be also observed, for example, in Collins-Miller experiments, like this in liquid spintronics experiment. So this is an experiment from like 5 years ago, and what they did in this is, and I should say that these kind of tabletop experiments are of course much more under control, because in the quark-gluon plasma there are all kind of other effects that you cannot really control, and you have to subtract the background and all that. So this is a dirty business. But here it's much more clear. What you have here is just, this is an experiment that you are all familiar with from undergrad. So if you just have if you have a tube with some fluid that is flowing in the tube, and if you apply some magnetic field, of course there will be some charge polarization. So charge will be, so you will produce some electric voltage, essentially because of the Lorentz force. The same thing happens in this. This is the experiment. what they did. This is the schematic description of the experiment. The same thing happens if you consider a fluid that is flowing in a tube in the presence of vorticity. Don't ask me how they produce vorticity. It is essentially coming from the friction at the walls. So there is, because of the friction at the walls, the velocity of the fluid there is less than the one in the middle. So this produces some kind of vorticity because of this gradient. And that vorticity aligns the spins of this fluid, which is, I think in this experiment, they were using mercury. So this is a fluid mercury. And those spins, then you can measure some spin voltage. And here in this picture that you see, what you see is that there is some kind of a spin density that is produced that is proportional to the vorticity in the fluid, and the spin current itself is proportional to the gradient of the vorticity. Okay. So these are the two main dispersion relations they found, and again, to be able to describe this an experiment like this, the theory of that should really be an independent theory that is based on energy momentum tensor and also the spin current, and this is kind of absent. Except, of course, there are some phenomenological models where people write down equations, but to derive this from first principles is absent. Any question? Okay, so this is the motivation, and I would like, I mean, the thing that I was just the point I'm trying to make is that, hydrodynamics can, in principle, be applied as a universal description to all of these different situations. Okay, so why hydrodynamics is so general that it can be applied, all from like a really wide range of scales, from cosmos to quark-gluon plasma, and including condensed matter and all that. The reason for that is that we understand in the modern understanding of hydrodynamics that we know, because essentially hydrodynamics can be understood as a theory of slow variables. So suppose that you have a quantum field theory, and you want to write down an effective description of this quantum field theory in the infrared. So a typical, typically the degrees of freedom in your system in a quantum field theory can be divided into two sets. There are these fast variables. These are non-conserved quantities. And there are the slow variables that are conserved quantities. So if you think of, for example, just some equilibrium configuration, of course, I will always be talking about finite temperature. So you have a plasma, it's at finite temperature, and you make a perturbation to this plasma. So if you make a perturbation, then it will decay because of dissipation. Typically, you have dissipation in your system. It will decay back to its equilibrium value. And this decay can happen in a very fast way for the non-conserved quantities because they can change their magnitudes in space. Okay, so they will decay very quickly. In some time, there is like tau relax. That all depends on the microscopics of the system. But there are, on the other hand, these conserved quantities, which cannot really change their magnitude in space. So they have to, if they need to decay back to this equilibrium value, and this happens at later times, because they can only decay by transporting their excess values for energy and momentum, for example, these conserved quantities, by transportation. So they will just be transported from one point to the other. And this will take typically much more than this decay of the non-conserved quantities. So this gives an idea. If you wait long enough, and if you consider just quite large distance scales, then essentially large wavelengths, in those limits, all of these fast variables will die, and you are going to be just left with the slow quantities, the conserved quantities, and you can write down an effective theory only for the conserved quantities. And these conserved quantities, once you write this effective theory, then you can make an expansion around this equilibrium, and you can essentially organize this effective field theory in derivatives of these slow variables. Okay. So here, this is the tau relax, is the relaxation time, and this is the mean free path typically. But in a system where, for example, a conformal fluid, you don't have these quasi-particle-like descriptions, and these quantities will be replaced by 1 over temperature. So that is a typical scale. So this is hydrodynamics. It's a theory of slow variables. That's why I think it is applicable to many different systems. And in principle, in particular, we would like to apply this to quark-gluon plasma. So in this particular case, so let me just directly go to the issue. So we want to write down a hydrodynamic theory for the quark-gluon plasma, or more generally in relativistic hydrodynamics that can be applied to other systems as well, for these slow variables, including the spin current. So these slow variables in this case is just the energy momentum tensor T mu nu, that's always there, and the spin current. Okay, the spin current here is just described by the 3 index quantity. So this mu nu index is, you can understand them as describing the orientation of the spins, and this is the flow direction. So you have a spin in one direction that is just given by this, perpendicular to this plane, and then it's moving in another direction, this lambda direction. And of course, these are just space-time generalizations of the concept of a current. This is relativistic quantum field. Okay, and I mean, from the way I explained this, it may sound like this is the first time that this is being done. Of course not. There has been a long literature on hydrodynamics with spin current, and there are very interesting early works. But most of these works essentially focused on a different aspect of spin current. For example, they were based on kinetic theory, or our work was based on holography. But what I would like to do in this talk is to start really from the first principles of hydrodynamics and construct this theory step by step. Okay, so. And the most systematic way of doing this, from what we know today, and this was available only in the last 9 years, is constructing hydrodynamics based on an action formalism. I told you that hydrodynamics can be understood as an effective field theory, and indeed we can do this directly from just essentially. You can imagine that you integrate out the degrees of freedom in your system and arrive at some kind of effective action. And this effective action, then you demand the symmetry principles that you have for this conservation of these currents, etc. And then you write down all possible terms in this effective action from which you can read off the hydrodynamic equations and the transport phenomena. So this is the basic idea. And let me just exemplify this in one particular case that is simpler. This is a charged fluid in the presence of external sources. So imagine that you have a charged fluid. And to be able to describe the energy momentum transport, you imagine again that you couple the system to some external metric. Of course, in the end, we are going to take the flat metric because we are interested in flat fluids in flat space-time. But you can think of this as just as a source, which, for example, this source, the gauge field, external gauge field, will couple to the electric current, and this just couples to the energy momentum tensor. So in this case, you have just two operators, two slow modes in your system, the energy momentum tensor and the electric charge, and those two operators are going to be coupled to these external fields, and then you just write down. So the effective action in this case is just to zeroth order in derivatives. This is the most general scalar that you can construct out of these two external sources. So that will give you the ideal fluid, and then you go on, you add the derivative terms, you just expand, you just write down the most general scalar out of these external fields and their derivatives, and then you just derive the equations of motion from there. You are guaranteed to get equations for the relativistic hydrodynamics. So, for example, if you impose the diffeomorphism invariance here, you're going to get the conservation of energy momentum in the presence of a work term that comes from the current itself. So this is just electromagnetic work, and from the gauge invariance you're going to get the conservation of the electric current. Okay, so this is the first two steps, and then you assume that there is some kind of a thermal equilibrium. There's a notion of thermal equilibrium in this system. So this is this you can understand as some kind of field theory in a curved space-time, and the thermal equilibrium, of course, is characterized by a time-like killing vector psi. So you assume that there is a non-trivial time-like killing vector psi, and from this, using this psi, you build the dynamical variables of your hydrodynamic system. So one of them is the magnitude of this psi is related to 1 over the temperature. The normalized psi vector gives you the fluid velocity. This is a vector, and then from this, the time-like killing vector, if you dot it the external source, you get the chemical potential in your system. So those are your dynamical degrees of freedom. There is 1 here, temperature. There's 3 here because this is normalized, and there is another one. So in total, there are 5 here. If you look at these equations, there are 5 degrees of freedom. You just count these indices. So there is 1 here, 1 degree of freedom. There are 4 degrees of freedom because this is a free index. So you can, in principle, solve these 5 equations by these 5 in terms of these 5 dynamical variables. And to be able to do this, what you need to do is to write energy momentum tensor and the spin and the current. In this case, it's not spin; it's just electric current in terms of these dynamical variables. So those are called the constitutive relations. I will give examples of those later. So you expand the entire thing in terms of these dynamical variables and their derivatives. You plug them in the equations of motion. You get an equation of motion for those particular degrees of freedom, which are now treated as functions of space-time. So that is the idea, and this is quite generic, as you can see. Now we would like to apply this to spin. In the case of spin, it turns out that it's better to use, instead of using metric, it's better to use Vierbein in 4 dimensions, and the object, the external source that couples to the spin current is, of course, something that you know. If you want to treat the spins of fermions, for example, in a curved spacetime, the way you do it is just by coupling them to spin connection. So this is spin connection. So instead of having a gauge field, an external gauge field, I will turn on a spin connection, a non-trivial spin connection, and instead of a metric, I will turn on a Vierbein. Of course, you can ask the question, well, they are not independent from each other, and I will tell you that they are independent from each other. That is when there is torsion present in the system. And as you will see, this is going to play an important role. So this is the basic idea. I think this is the bottom line. If you don't follow the rest of the talk, that's okay. So this is what I'm going to be doing. So based on this idea, I will just develop the theory from now on. But are there any questions so far?
There is a question in the chat, by the way.
Oh,
yeah, there is a question in the chat.
Let me see. I'm not following the chat.
Well, let me just read it.
Okay. I can see. Is it exactly the chemical potential that we know in thermodynamics or something? Yeah, it is exactly the one. Yes, Savaş. Yeah.
Okay,
It's exactly the same chemical potential.
I just write it in chat, not to cut you, right?
No, thanks. So I just I'll check the chat like from time to time. That's great. Okay, so now let me move on. But there should be this question because when you study quantum field theory, you learn that there's a big ambiguity in the definition of the spin current. In particular, the spin part of the total angular momentum is not well defined. You can always swap between these 2 different degrees of freedom by making what is called a Behm-Fante-Rosenfeld transformation. Because when you write down the total angular momentum, the equations of motion here is just the conservation laws are the total angular momentum is conserved and the energy momentum is conserved. But you can always make a transformation, which is called, again, Behm-Fante-Rosenfeld. So you introduce some 3-index tensor, which is antisymmetric in the +2 indices. This is, by the way, it's important that spin current is antisymmetric in these 2 indices, obviously, because it defines a direction perpendicular to it for the spin. And here, the same thing, if you just consider some transformation by some arbitrary 3-index tensor, where the energy momentum transforms as a derivative and the spin current shifts like this, you can always choose this phi to be the same thing as the original spin to kill it. You can transform the entire spin degrees of freedom in the total angular momentum inside the orbital momentum. So that is true. You can do this. And the claim is that this ambiguity will be completely removed by torsion. And this is something that you can understand easily, because torsion, what it is essentially it tells you how these planes that are that you move along a geodesic or move along a curve in a curved spacetime, how the planes are rotating. Okay, so for example, the curvature will tell you how the connection itself will tell you, for example, how these planes are flowing, but just like flowing along this gradient along the curve. But the torsion is telling you how they are kind of like reorienting themselves. So they are coupled, obviously, like from at least conceptually, you can understand that they are coupled to the spins of these of the particles that are living in the space-time. So from a more mathematical point of view, there you can understand it as an antisymmetric part of the affine connection, or you can also understand it as this the covariant derivative of the Vierbein. Okay, so this is a covariant derivative of the Vierbein with respect to the spin connection is torsion. And typically, what we do is we consider, of course, systems where there is no torsion. So we set torsion to 0. But what I will tell you now is that if you don't set torsion to 0, you are going to get an independence between the Vierbein and the spin connection, and that ambiguity, this Belinfante-Rosenfeld ambiguity that I mentioned here, this one, will be completely fixed so this kind of, you can understand it as some kind of a gauge freedom, and that gauge freedom will be completely fixed by considering these fluids in the presence of some external torsion. So let me tell you how this works. So consider a quantum field theory in a non-trivial Lorentz representation, like fermions, for example. You integrate out all these canonical degrees of freedom, you end up with the effective action that is only a functional of Vierbein and the spin connection. And then you can define the energy momentum and the spin current by taking variations with respect to these two. So variation with respect to the Vierbein is going to give you the energy momentum, and the variation with respect to spin connection is, by definition, this is the spin current. But now, if you now demand that the metric and the spin connection are dependent, because by setting the torsion to 0, typically there's no torsion, that we never consider torsion. In this formalism, when we write down a quantum field theory, we always implicitly assume that there is a dependence between the Vierbein and the spin connection, because they satisfy this equation. If you use this constraint, when you vary your effective action with respect to the Vierbein, you get precisely this term, because this is going to come from just taking a variation of this with respect to E. Now you have from variation of this with respect to E. So the first term is the canonical energy momentum tensor, and the second term will come from variation of this with respect to omega first, this W, the spin connection, and this variation of the spin connection with respect to E, because they are dependent. So this is going to give you exactly this contribution. So this you recognize now from this Belinfante-Rosenfeld form when you set phi to S to kill it. This is coming from there. And this comes just because you have you demand that this is 0, the right-hand side is 0. So the first thing that we did in this paper was essentially, I think this was understood maybe before, but it was never really spelled out clearly in the literature. So the first thing that we did was to make this clear, that this Belinfante-Rosenfeld ambiguity can be removed essentially by turning on an independent torsion term. Okay, so this is a non-trivial external source, which precisely sources your spin in your system. And in the end, of course, what you want to do is to keep to send the torsion to 0. And you can ask me the question: if you assume that it's non-zero in the beginning, and then at the end you send it to 0, what do you gain? What you gain is that you make sure that you don't lose any terms in the derivation of your effective field theory. It will become very important, as you will see. I will try to convince you that this, doing it this way is important. But the bottom line of this is that, to remove all these ambiguities and to make sense of this theory, you have to turn on torsion. And but the torsion, you should understand it as some kind of a bookkeeping device, which you send to 0 in the end, exactly the same way as you would do for the energy momentum tensor. There also the way you define it unambiguously in hydrodynamics or general relativity is to couple it to a metric, some non-trivial metric, and then in the end you send the metric flat. But this is the same thing for torsion. This is what I'm saying. So torsion, you just first consider some non-trivial torsion, and then you send it to 0. Okay. So in practice, it will be better to consider contortion rather than torsion. So contortion is defined as the part of the spin connection that gives rise, that vanishes in the absence of torsion. Okay. So in the first part, you can divide the spin connection into two parts in general. So the first part is going to be just given by the derivatives of E, which is just solving this equation. Okay, so this part. So the solution of this is going to be omega ring here, this one. And in the presence of torsion, there's an additional term, which is in one-to-one correspondence with torsion itself, but it's called contortion. So it's a different combination of the indices. But for me, it doesn't matter. So we can also do the entire thing in terms of torsion, but this will be more convenient. So let's focus on contortion. In the end, as I said, eventually I will send contortion to 0. But you can understand already, I can tell you why it is important to keep it first non-zero and then send it to 0 in the end. Because now imagine that you write down an effective field theory. Now it's in terms of all these external sources. Here now it includes, for example, this contortion piece. And the variation, the spin current you obtain by taking variation of this with respect to the spin connection. So the same thing as taking variation with respect to the contortion. So that will give you a contribution to the spin current if you take variation of this with respect to the contortion. But if you consider, for example, or linear terms in K, if you send those terms to 0 in the end, you are going to get no contribution to the spin current. But if you first take a variation with respect to K, you're going to get a coefficient of that term, and then you send K to 0, you will still get a non-trivial contribution to the spin current. And those contributions are going to be important for the consistency of the theory. So that's why it's important from the onset that you make a systematic expansion, consistently treating all the degrees of freedom in your system, and this boils down to keeping finite torsion. But well, as I said, this was only for for me it's like a bookkeeping device. But for certain condensed matter systems, this is more than a bookkeeping device, because for example, in graphene, this contortion in this torsion in those systems describe what is called dislocations. So you have a dislocation, for example, in the atomic structure of a graphene like this, and this dislocation in the limit IR limit, when you describe this entire system by some kind of quantum field theory, those dislocations do not they're relevant in the IR. So I mean in the UV, so they are present in the IR. So these dislocations are going to be an important part of the quantum field theory, and they are precisely described by this notion of torsion. Because this dislocation, you can understand the inability for this vector that when you follow this this vector around this loop, the inability to close. So you define that it closes when you have an hexagon, and when you have a pentagon, or when you have 7 atoms here, then it doesn't close. So it's plus or minus. So there's a Burgers vector, and this Burgers vector can be understood as torsion, because torsion by definition is just you take two vectors perpendicular to each other, for example, and then you parallel transport each of them with respect to the other, and then if they don't close, this difference is precisely what is proportional to torsion. So all I'm saying is that, I'm not going to be talking about these kind of things in this talk, but there's an application of, torsionful hydrodynamics. There's an application of this in principle to dislocations in graphene as well. So it already gives an idea that maybe you will be able to generate spin currents by using dislocations in a graphene. Okay, so that may be an interesting application to condensed matter, but I'm not going to talk about that here. Okay, so let's get down to business. Let me now, after all this introduction to the degrees of freedom that we have, the kind of external objects that we have to keep, and the degrees of freedom in the game, let's now write down the hydrodynamic equations. So again, this should be done in a systematic way, and the best way to do, granted to us by this action formalism of hydrodynamics, is again to require invariance of this effective action under certain local symmetries. So one of them is the diffeomorphism, and that is essentially just the transformation of your external sources, like the Vierbein and the spin connection, by some diffeomorphism transformation described by this C here, and that diffeomorphism transformation is implemented by the Lie derivatives of your external sources. But on top of this, when you turn on this Vierbein, when you're in the Vierbein formalism, you also have this local Lorentz transformations, and your theory by consistency should be invariant under local Lorentz transformations as well. And those local Lorentz transformations are just transformations that that rotate the Vierbein, and under which the spin connection transforms as a gauge field, just like this is the covariant derivative. Okay. So, and if you do this, those two, if you impose those in your effective action, then you immediately get two equations of motion. One is the energy momentum tensor conservation or non-conservation in the presence of these sources, and the other one is the equation of motion satisfied by the spin current. So let me tell you more about these equations. So for example, in this one on the right hand side, this is very analogous to this equation that I showed before. This one, where is it? Yeah. This one. It's just a non-conservation of the energy momentum tensor in the presence of an external source, external force. So in this case, the force is given essentially by the current, the product of the current and the field strength of the external source that couples to that current, this one. In this case, this is exactly the same thing as you can see. You get the same equation. Here you have the current, the spin current, and this is the field, this is the field strength of the external source, that is the spin connection that couples to this. Because you can understand the Riemann tensor as d of omega, d omega plus omega wedge omega. Okay. So this is totally analogous to electromagnetic force, and this you can also understand this as totally analogous to the torsion part of this story. Here, this is essentially, again, you have contortion, and so this is the antisymmetric part of the energy momentum tensor. This is essentially the part of the current, and the thing that the field strength of the external source that couples to this, the antisymmetric part of it, is going to be the contortion. Okay, so this is, you can understand it also like that. Now this is one equation, and let me tell you already that in the end, when we send the metric to flat metric, this will drop. When we send contortion to 0, this will drop. But it will be important, along the way, that you should do only at the end. So they will contribute to 2-point functions, 3-point functions, whatever that you obtain by expanding, by taking variations of these equations. So the same thing for similarly for the energy for the spin current, you have an equation like this. So on the right hand side, again this term is going to drop when we send k to 0, but this will not. So this is important. So this is the antisymmetric part of the energy momentum tensor, and then we see immediately that this sources spin, and this you can understand, of course, from this Belim-Fenter-Rosenfeld ambiguity I mentioned before. So the bottom line is that you have these precise equations to solve, and how do we solve them? We have 4 equations here because this index is free. We have 6 equations here because these 2 indices are free, but they are antisymmetric. And we need essentially 10 degrees of freedom to solve them. So those 10 degrees of freedom are these ones. So these are the 10 dynamical variables. One of them, so assume again that you have a hydrostatic limit, you have some kind of a thermal equilibrium in the presence of sources, and you can define, so that means essentially that implies that there's a killing vector, time-lag killing vector. By using the time-lag killing vector, you can construct those 10 dynamical variables. One of them is going to be the magnitude of this killing vector psi, that's just temperature, and the other one is going to be the normalized killing vector itself, contracted with the Vierbein. So that gives you the fluid velocity. And the most important one is the one that you obtain. This is the complete analogous to the chemical potential. This is the one that you obtain by contracting the spin connection with the time-lag killing vector. So this is complete analogous to the electric potential that you obtain by contracting these 2 quantities in that example. Here, this is for the spin. So there are like 6 quantities that you can construct. Those we call spin chemical potential. So there are 6 of them here, 3 here, 1 here. So this is in total 10. So we can solve now. The next thing is going to be writing down the constitutive relations for the energy momentum tensor and the spin current in terms of these quantities in the most general possible way. Okay, so that's the game. Okay, let me just check the chat. Anyways, can you see anything in the chat? Nothing. Okay.
No, there is no question.
Okay. So, good. Now let me first focus on the hydrostatic equilibrium. So hydrostatic equilibrium is a thermal equilibrium in the presence of time-independent sources. So we can understand this as like the atmospheric pressure, for example. There is the atoms, the gases in the atmosphere that is in hydrostatic equilibrium in the presence of some external source, which in that case the external source is of course the metric, right? So they are kind of like, and you can understand that in that case they are in the presence of an external source. These gases are in thermal equilibrium because they don't move unless you just blow a wind or something. But and there's a notion of thermal equilibrium. There's a time like killing vector, etc. But there should be this equilibrium essentially imposes some conditions. For example, the acceleration in the system should be related to the gradient of temperature and things. That's why the temperature is going to decrease as you go higher and higher in the atmosphere and things like that. So there will be some non-trivial physical relationships between the dynamical degrees of freedom and the external sources. And those can be derived completely, again, in a systematic way, by demanding that your external sources are time independent. So they are independent under the Lie derivatives of this time-like killing vector. So these are two non-trivial equations. This is just when you expand them, they are non-trivial equations. And when you essentially work them out, what you find is that from the first one, you get exactly the thing that I mentioned already, that the acceleration in the system, it will be related by the gradient of the logarithm of the temperature. And from this equation, you get something new by demanding that the spin connection is time independent. You get a relationship between these spin chemical potentials and these other quantities that we know. So this is just to tell you that these spin chemical potentials are not completely some extraterrestrial weird alien things. We can go to the hydrostatic equilibrium and there you understand what they are. So suppose that forget about torsion, just fix torsion to 0, get rid of torsion. There in that limit, what you understand is that spin chemical potential is nothing else but this combination of these two terms. One of them depends on acceleration in your system, and the other is what is called the vorticity. So this combination itself is called thermal vorticity. And this thermal vorticity is precisely the object that has been playing the role, the major role in deriving this global spin polarization I mentioned in the beginning of the talk when I was motivating this problem. So in those observations, when the people observed this global polarization of the hyperon particle, they understood it. They understood that was coming from thermal vorticity, and they wrote down some simple phenomenological equations. They didn't derive that, but they wrote down those equations, and essentially from those equations and from the fact that how much polarization was there in the system, how much was observed, they they inferred the value of the vorticity, the thermal vorticity rather, and they found this astronomical number. Okay, so that is what they did. And here what I'm telling you is that in this hydrodynamic picture, it's quite natural because this is one of your dynamical degrees of freedom, which becomes in the hydrostatic equilibrium exactly this thermal vorticity. But these equations, I mean, hydrodynamics tells you more. It tells you much more than just the kind of simple-minded phenomenological equations, because it tells you that if you go beyond hydrostatic equilibrium, so now imagine your quark-gluon plasma, which is not in equilibrium, right? It's expanding. It just goes through a completely wild phase, the initialization of the hydrodynamic, the evolution. That was essentially a completely non-equilibrium, chaotic phase it goes through. But there, if you assume that hydrodynamics still works in that expansion, this picture is going to provide something more, because in that case, if you go beyond hydrostatic equilibrium, that this relationship doesn't hold anymore. So the spin chemical potentials are not fixed to be what's called the thermal vorticity, but it becomes something completely independent. It becomes an independent variable out of the equilibrium. So what you really have to do is to treat it completely independently, solve these hydrodynamic equations of motion, and from that spin chemical potential that you obtain, you just work out the polarization. So that is the right way of doing things, I think. Okay, so the upshot is that these things, so this spin chemical potential out of equilibrium should be completely determined by solving hydrodynamic equations. But for that, we need to first write down the constitutive relations because the hydrodynamic equations are these equations. I have to expand the energy momentum tensor and the spin connection in terms of those dynamical variables, these 10 dynamical variables first, and then plug it in these equations. I'm going to get an equation for each of these dynamical variables. And to solving them, then I can compute. After solving them, I can compute the polarization. Okay, so that's the plan of the rest of the talk. Now, so the point is to construct the most general hydrodynamic action from these dynamical variables that we have. To do this, the systematic way of doing it is just to start with the spin connection, and first of all, you can decompose it into two components. One of them is the time direction of the spin. So there is an index, mu index here, space-time index. You from this object, you can construct a time-like part by contracting it with this time-like Killing vector. This is going to be the spin potential, and all the rest are going to be spatial components of this object, and those I'm calling spatial torsion. And spatial torsion, okay, so they will be present in the system, but I treat them independently because the most important part is just this spin chemical potentials. So let's focus on this first of all. Now, this is a 6 degree of, there are 6 degrees of freedom here. This is antisymmetric. So what you can do is you can construct, and also you are given this time-like Killing vector. Okay, so this UA or psi A, or just like normalized it, is UA. So this fluid velocity. So by using this fluid velocity vector, you can decompose this further into two vectors. Okay, so one of them is just I'm calling it the small m. The other one I call it capital M tilde. You can think of this as there is to make an analogy with the field strength in quantum, not necessarily quantum, just electrodynamics. You have so think of this as the field strength. You have an electric field and you have a magnetic field, exactly the same decomposition. Here we can do the same thing. So this is like you can think of this part as some kind of electric spin potential. This is something like a magnetic spin potential. Each of them has 3 degrees of freedom because they're perpendicular to you. Now then the rules of the game become very clear. What we have to do is to write down the most general scalar that you can construct out of these variables. So temperature is a scalar itself. This, if you have 2 vectors, what you can do is you can dot this to itself, you can dot this to itself, or you can take the cross product of, the dot of these two terms, something like this. So there is nothing else you can do. So this will give you at the level, if you ignore all the derivative corrections, right? So if you just ignore all the derivative corrections, this is what I'm calling the ideal spin fluid. So this will be just the most general function that you write down. This most general function should be given in terms of those 4 variables. And then, okay, so you can consider the gradient corrections, which we will do later. So let me first tell you what you get from the ideal spin fluid. So just from the fact that you can write down this function, so you just write down P as a function of those objects, you get all these non-trivial Gibbs-Duhem relations. This is the beauty of this, action formalism, if you want, because we just take this. I'm calling it a pressure term because I'm considering some extensive systems. In the extensive systems, Lagrangian is proportional to pressure, and so what you can do now, you just take this effective action And I told you already that the spin current and the energy momentum tensor are defined as variations of this thing with respect to the sphere bind and spin connection. And if you just apply that to this pressure term, you get these nice relations. You immediately get two expressions for the energy momentum tensor and the spin current, and it looks like this. So this part, if you have studied relativistic hydrodynamics, or in the context of general relativity, you will recognize this part, this piece. This piece is just the ideal fluid in the absence of any spin or other kind of charges. So this is the energy term. This is the pressure term, and this delta is just the projector perpendicular to the fluid velocity. This is the fluid velocity. But now you get these two additional terms, essentially coming from those spin chemical potentials, and you get this. First of all, the coefficient of this term is the spin susceptibility, just given by the derivatives of this pressure with respect to this spin chemical potentials, and the term itself is you can understand it as some kind of a spin pointing vector. This is really like the cross product, because this m beta gamma, I define it as this Poincare dual of this original vector I had in the previous slide. So this is exactly like m times m cross m tilde. That's like a spin pointing vector. In particular, it doesn't have any time component. It's just like momentum. Okay, so this contributes, the spin contributes, the spin chemical potentials contribute to the momentum, overall momentum in the system, and it's given by this term. Okay, so this is something new. But not only that, but you also get the relationship between energy, pressure, and the spin densities in your system. Another thing I just forgot to mention is that you get, for the spin current itself, you get that it's proportional to some coefficient, which is spin density, which is something that you have to find by solving the equations of motion, and the fluid velocity. And this is, of course, something that you would expect. This is exactly like an electric charge. We have a charge density times u lambda. That's the ideal current. It's exactly of the same form. And there's also these relationships. Well, now this you understand the Gibbs-Duhem relation between energy and pressure in standard thermodynamics. I learned it all from Mahmut Hoca. But now I added this term after 30 years. So there is this term, the spin chemical potential times the spin density. It also contributes to the energy in the system, because spins store energy. And the spin density itself can be, by solving this system, just you're doing this calculation, essentially you can obtain it in terms of the spin chemical potentials in this particular way. It's complicated. I'm not going to read it off, but it's essentially it's all given in terms of the how it depends. If you know how this pressure depends on your spin chemical potentials, you will know what the spin density is. So it's all given in terms of these quantities, the spin chemical potentials m and capital M tilde, or their Poincare duals. They're completely equivalent. Okay, so now let me ask you, before going further, let me ask Suat maybe how much time I have, so I can cut it short. I did ask. I cannot hear.
Yeah, Umut, did you ask something?
Yes, I'm asking like how much time I have.
Yeah, let me just check. 12 minutes.
Okay, good. Okay, so now this is getting more technical, but I will cut the technicalities. It will become a little bit more technical, and then I will apply this entire formalism to experiment. So let me. But as you can see, this is already technical. This is getting complicated already at the zeroth order in derivatives. If you go to first order in derivatives and you apply this derivative expansion, again, let me repeat the rules of the game is to construct the most general functions out of all these dynamical degrees of freedom that you have in your system and their derivatives. If you add a derivative to each of them, we are going to add a new index. And now you have to construct all possible ways, all these indices, it's really getting a very complicated game. It's like, playing Lego with, 200 different pieces of type of Lego pieces. It's really getting very complicated, but that's okay. But we just, this was the first paper in the subject, so we just simplified our lives by essentially assuming that there is a conformal invariance and parity invariance in the fluid. Let me just close this. Yeah, okay. All right. So if you do this, first of all, what you get, the way you implement conformal invariance in this setting where you describe the hydrodynamics by coupling your systems to external, placing your quantum field theory on some curved background with torsion, is to demand Weil invariance of your action. And Weil invariance is just this dilatation, essentially, this transformation of your field line. And if you do this, essentially what you find, if you demand that your action is invariant under this transformation, you immediately get a word identity, which is the conformal word identity. So that relates the trace of the energy momentum tensor to a particular derivative of your spin current. Okay? It's a modification of the usual conformal word identity that you're familiar with, where the right-hand side becomes 0 in the absence of spin. And if you just, now what you do is you go through the same. First of all, let me first assume conformal invariance and parity invariance and see what we get at the ideal fluid level. And there you get exactly these relations. So you get, for example, the energy of the system is precisely given as a coefficient times T temperature to the power 4. This is just from essentially all these terms you can obtain by dimensional analysis. Okay. And the pressure itself again is T to 4, but there are corrections. This correction is coming from the spin chemical potential square. And one thing that you see is that this conformal word identity is going to be violated for the other term, this small m term. So the small little m, remember, I'm now talking about this one, this capital M tilde, but the small m, this one, is going to violate this identity. So you set it to 0. That's why it simplifies your life. Demanding this extra constraint kills many terms in your expansion and just makes it life much simpler, so you can write down all these equations precisely. So you have this energy with this correction, pressure with this correction, and you have the spin density now is given completely in terms of this chemical potential, etc. So that becomes clear. And then you can go ahead and write down the most general correction to the ideal fluid by considering terms first order in spatial torsion. I'm treating the spatial torsion as first order in this expansion. And then you get 3 terms. In this conformal and parity invariant fluid, there's only 3 terms with 3 coefficients, which we cannot compute. I'm not going to get into details of these terms. So all of them can be constructed out of the spatial torsion. But let's focus now on the corrections to the ideal spin current. So this is the ideal spin current, and you get all these corrections from the first order hydrostatics. One of them is this, the other one. So all of these 3 terms, when you take variation with respect to the spin connection or with respect to the contortion first, it's the same thing. You get all these 3 terms. Okay, so the 2 of them are proportional to the spin chemical potential, and that will just vanish in the limit when the spin chemical potential goes to 0, or when it's given completely in terms of this vorticity that I mentioned before. It will be completely fixed. But there's a new term. This is the kind of term that I was mentioning, I was referring to in the beginning of the talk, but I was saying that there will be those kind of terms that are linear in contortion, and you first take variation and then set k to 0. You're going to still get some non-trivial contribution, and here it is. This is the one. Okay, so this is very important for the consistency of the entire picture. It's kind of a universal unsourced component because it doesn't depend on the spin chemical potential. Okay. So in view of time, let me go faster because I really want to show you the application of this to particle physics. There will be all these non-equilibrium corrections. So far I was talking about hydrostatics, which is essentially just thermal equilibrium in the presence of sources, but now I can also go beyond hydrostatics. I can consider the full system, hydrodynamic system, in a non-equilibrium state, and that will give additional corrections to your spin current and the energy momentum tensor as well. And again, for this conformal and parity invariant fluid, you get all these 5 different terms with the associated transport coefficients, which I'm not going to explain. And all these terms can be constructed. Apart from this one, this is coming from shear tensor. The others can be constructed from the spin chemical potentials, but the difference between the spin chemical potentials and the vorticity and acceleration, because those are the ones that was vanishing. Those are the combinations that vanished in the limit when you take hydrostatic limit. So this equation, when you expand mu, where was it? Yeah. When you expand mu like this in terms of m and capital M tilde, if you substitute here, you're going to see that in the absence of torsion, you're going to see that certain combinations of this m and a and capital M tilde and vorticity vanishes in the hydrostatic equilibrium. So if you go beyond hydrostatic equilibrium, if you go to non-equilibrium physics, then those differences become your dynamical variables. So this is what I'm defining here, those differences. And this is completely given in terms of those differences. Let me skip all the details, but just to show you the equations of motion that you get after writing down all these constitutive relations and just substituting them to your equations of motion and expanding them, you get an equation. This is some kind of a conformal derivative. I'm not going to explain what it is. The temperature is a function of space and time. You obtain it by solving this. This is the second order equation. So this is a shear tensor, which is essentially given by the traceless transverse combination of the derivative of the fluid velocity. And that includes a derivative also. There is another derivative here. So this is a second order equation, a differential equation for your fluid velocity u. And these two are, again, differential equations. First order differential equations for your spin currents, for your spin chemical potentials. So this is a complicated set of equations which depend on transport coefficients. As you can see, all these coefficients are terms that I cannot fix by doing hydrodynamics, so they should come from microscopic physics, some quantum field theory calculation, which we don't have. And on top of that, you need to know the initial conditions. Say, for example, in this heavy ion collision, when you collide two beams, and there's a complicated system, and then it starts, the hydrodynamic evolution starts. When it kicks in, the hydrodynamics, you need to know the initial conditions at that point. So initial density of temperature and energy and your fluid velocity as a function of space-time and all these chemical potentials, etc. So all of these things are missing. We don't know. But still, I claim that you can apply it to heavy ion collisions and get a non-trivial nice answer. Let me tell you how this works.
4 minutes left.
4 minutes is good, yeah. So let me tell you that's my record. I mean, I'm usually like up by typically half an hour over the talk. So this is much better. Now let me tell you what people were doing before. So people have been doing this. So they were just essentially just following this picture that in an off-central collision you have these two colliding beams. They produce the quark-gluon plasma in between, and together with some kind of non-trivial vector velocity gradient, because this part of the quark-gluon plasma is moving faster than the center, and this gradient essentially is producing some kind of thermal vorticity at finite temperature. And this thermal vorticity, because of the spin orbit coupling, leads to polarization, and which you compute, you compare with the experiment, from which you infer the value of this thermal vorticity. But I was telling you so far, and that was really the bottom line of this talk, I think, that this picture is true only at hydrostatic equilibrium. And this system is, to me, it's really far away from hydrostatic equilibrium. It's not like atmosphere that is standing there. it's really, you know, this is expanding. It's you know, especially at the early stages of your hydrodynamic evolution, this is completely non-equilibrium. But you can still apply. There are many indications of this. You can still apply the full hydrodynamics, not hydrostatics, but hydrodynamics. And in hydrodynamics, the idea then is the following. So this is an equation that has been done before, that has been derived before. So this is essentially telling you, if you know the spin chemical potential in your system, in that case, it was given by thermal vorticity. If you know this object, then you can obtain the global spin polarization by applying this is the Pauli-Lubanski vector. Okay, so for a particle with massive particle, the spin of that massive particle is given in terms of momentum and the spin density like this. And these complicated integrals are essentially just so what happens is that, you know, this quark-gluon plasma expands and then it becomes confines, the deconfinement transition, and it produces all these hadrons. So this is it happens at some kind of a fixed temperature around like 150 MeV. So that temperature, that T constant, defines a freeze-out surface for you for the quark-gluon plasma. At a certain time, this temperature drops at that time. So it's like a codimension 1 surface. And you can integrate over that codimension 1 surface of your on your quark-gluon plasma, including the spin chemical potential, and include the Boltzmann type distribution for these hadrons, and you get the spin polarization. So, long story short, this is an equation that you can derive from kinetic theory. You don't really need to. We didn't need to derive it. The only thing we will need in this game is to solve these equations, obtain the spin chemical potential, plug it in here in this formula, and compute the polarization. So we did this for a Bjorken flow. There is a very high symmetric flow. Let me not get into details of this, which is essentially just boost invariant flow with also translational invariance in the transverse directions and some Z2 invariance along the beam. The nice thing about this is that you don't really need to go and solve all these equations, because in that case, you know already what the fluid velocity is. It's just the time component is 1, the rest is 0. The temperature also can be obtained like this. So there's a shear viscosity term, and there's it decays as a function of proper time like this, etc. But this is a standard thing. Bjorken flow has been used in many applications of hydro to quark-gluon plasma. So that's not a completely wild thing to do. But what you do this, when you do this, you don't get spin just because of initial. If you don't, break the rotational invariance around the beam, you don't get a non-trivial spin polarization. It just vanishes. To get that, you need to break it by essentially by this kind of picture, by demanding that you have a non-trivial component of your fluid velocity at an initial time that is proportional to the what is called the impact parameter and some kind of a momentum in the x direction. So this is the momentum in the x direction, Qx. Okay. So you do this, and you plug it in the equations of motion. You make another approximation, essentially, that the shear viscosity is small compared to your temperature. And then you can obtain, by solving those equations, you can obtain the spin chemical potentials. And once you have that, you can plug this in, integrate over the spin freeze-out surface, and you get this nice curve, which matches the data. This is just showing now, again, the original picture I showed was average polarization. That was like for two different hyperons and anti-hyperons. But this is the average polarization as a function of the center of mass energy. And so we are happy, this is essentially, I'm not saying that, all these things that we described is explaining the data. In some sense, it is explaining, but it is, to me, it's more like a proof of principle that, this thing is in the right track. But then, of course, you have to go back and question all the approximations that went in this calculation. Okay, so let me skip this. Let me skip all the holography business. Let me just come to a summary. So what we have done is a systematic study of spin transport in relativistic hydrodynamics. And I told you told you how to derive the hydrodynamic equations and the constitutive relations up to second order in derivatives. And I think I hope I convinced you that torsion, this differential geometric notion of torsion, plays an important role in this entire construction, because this is an independent, it plays the role of an independent source to spin. And then the spin potentials, the spin chemical potentials, are the dynamical variables out of equilibrium. You can solve your equations for them, match with data, you see some nice description, and there are all kind of some match with the observation, but then there are all kind of questions that remain unanswered. One of them is, for example, the transport coefficients. How do you compute the transport coefficients? So there are these new transport coefficients associated to spin transport. How do we compute them? How do we get them? Well, holography is one way. But okay, I mean, I'm going to leave it to questions. If you have any question, I can tell you how to obtain it from holography. I'm not going to talk about that today. So, so I will just leave you with this outlook, and thank you for your attention.
Yeah, thanks, Umut, for such a beautiful talk. I think we can start the questions session and receive a couple of questions or comments. Are there any questions, comments? Yeah, Aydın.
Hello.
Hi.
This is Aydın Keser. I'm from Sydney, actually, so it's a bit late here, but thank you very much for the interesting talk. So it keeps everybody awake. I'm a condensed matter physicist, and I was really interested because I recently talked to Sadamichi Maekawa, who is conducted the mercury experiment. I have very short comment and a question. My comment is that the physics is basically Larmore's theorem. So if we go to non-relativistic system, what happens in a condensed matter system, for example, is that electrons get stuck in fluid vortices and they equilibrate in these co-rotating reference frame. And if you jump on the co-rotating reference frame of a vortex, then the rotation appears due to Larmore's theorem as a magnetic field. This magnetic field both couples to orbital and spin degrees of freedom of electron, because it's only the total angular momentum that is a generator of rotations. Therefore, you get alignment of electron spin with an effective magnetic field that is due to vorticity. But here's the catch. For this to happen, you need a spin-orbit coupling force that equilibrates the system in the co-rotating frame.
That's right, yeah.
My question is, in the condensed matter system, it is governed by two things. One is the spin-orbit coupling force in the material, and the second is the kinematic viscosity or electron-electron scattering time. And depending on the interaction between the two, this equilibration time of spin might be very long, in which case it does not equilibrate. So in order to equilibrate on a static frame, you need strong spin orbit coupling and some friction.
That's right. Yeah, so very good. So, I mean, if I understood your question correctly, so how in this system the same thing is happening? Well, there are two different things. But I can answer this in the context of the quark-gluon plasma. It's similar. You have a spin orbit coupling in QCD, and that spin orbit coupling is playing an important role. And at the same time, there is viscosity. So this is the last part of the talk I had to skip very quickly because not this one, but this here. So here, for example, this is the kinematic viscosity. Okay, so this is precisely the kinematic viscosity. I'm assuming here it's small because to be able to derive these analytic expressions, but this still is important. It's playing an important role. Without that, you don't get equilibration essentially. That is true. But in terms of so it's a very good question about the equilibration time. So the equilibration times, I don't know. I'm just assuming that you can describe. So this is a working assumption. I'm just assuming that spin degrees of freedom and the fluid, the background fluid velocity can be treated as some coupled system in a limit, in some kind of a late time limit, essentially, where you can treat them as near equilibrium or out of equilibrium. So this formalism applies also out of equilibrium, by the way. It can be out of equilibrium, but it's still, these are the right degrees of freedom. This is what I'm assuming. So, and you can of course question this. You can say, for example, in this quark-Coulomb plasma, it doesn't have too much time. It just, it happens everything happens in like 10 to minus 22 seconds. So it just equilibrates quite fast, but then it decays very fast. So maybe the spin degrees of freedom are never going to be able to equilibrate in the system. That's true. In that case, I cannot really describe the spin degrees of freedom as some kind of coherent, in terms of a coherent spin flow, spin current. And then the entire formalism will break down. But matching the data tells me otherwise, essentially. It shows that, this approximation may still be working here in this particular system. And then coming to maybe another question that you asked is that apart from this particular system, if you want to apply, because I wanted to motivate this from a more general point of view, that saying that this is a general description of relativistic spin hydrodynamics. So where is the spin orbit coupling, for example? That is in these hydrodynamic equations. It is, of course, you don't have any access to microscopic physics, but it is kind of you can understand where it is coming from. It is in this effective description. It is described by these. I'm just going back to the equation of motion. Where is my equation of motion? Here, this term. So the spin couples to the antisymmetric part of the energy momentum tensor. This is really the spin orbit coupling. It is it's manifestation of the spin orbit coupling in the hydrodynamic regime. Yeah.
Okay, but excuse me, just another small question. So on top of this, so I'm assuming that you have a strong spin orbit coupling in this system.
Yes.
Strong spin orbit coupling and small viscosity, because this is almost a perfect fluid, right? So it satisfies the viscosity to entropy density almost minimum allowed by quantum mechanics.
Yes, that's right.
Spin orbit coupling and small viscosity means that you can equilibrate, but on top you also have magnetic fields and probably spin dephasing mechanisms coming from other stuff.
That's all of that is possible. You see, this is just the beginning of the story. So on top of that, I agree with you. You need to really see, for example, to see this difference between these different particles, the polarization of these two different type of particles, these red ones and the red curve and blue curve, that is coming from magnetic fields. As I said, I'm setting magnetic field to 0 and just treating this, just trying to get the average of those two. Okay. Because it's hard. It's just because it's hard, and also because there is some finite conductivity in the system. So the magnetic field, even though because of conductivity, the magnetic field prevails for some time, it decays faster than the vorticity. If you're really looking at late times, where this freeze-out mechanism is taking place, where you produce this spin polarization, the magnetic field is really much weaker than the vorticity. Again, by assumption, but it's a reasonable assumption. That's right.
But if I want to see this signature in the gravitational wave of a neutron star has an enormous magnetic field.
Right. No, the quark-Coulomb plasma also is an enormous magnetic field, but it decays very fast. But yeah, you are right. So you see, it's a good question. These are all questions beyond me, because well, I can answer there. That's a very good question, but we will have to wait a lot for that to happen, to be able to read, spin currents from gravitational waves, because you need the Einstein telescope. The gravitational waves, you you observe in the initial phase, in the pre-merger phase, is not going to carry any interesting information about transport. It's not going to happen. It only tells you about the deformation of these neutron stars, etc. But it doesn't tell the equation of state. It tells you about the equation of state, but it doesn't tell you anything about the transport. For the transport to happen, those neutron stars should really merge, and then you will have to have this produce some quark-gluon plasma from, and maybe in the future, after in 10 years time, we're going to have Einstein telescope, and then it's going to take another 10 years or whatever to collect data. Maybe in 20 years we can be asking this question, but it's too early. Yeah.
Thank you very much, and I would be very happy to discuss further because we are planning an experiment on.
Okay, yeah, I would love to hear about it. Yeah, that'd be great. Thanks. Okay.
Yeah. Any other question, comments? Yeah. Umut, it seems there is no more question. Yeah. So we can stop here.
Thanks.
Yeah, thanks a lot for having time for this nice talk.
Thank you. Thank you for the invitation.
Yeah.
So hope to see you next time.
Yeah.
All right.
Yeah. See you.
See you guys later. Bye. Thank you.
Bye. Bye.